All right. How are you guys doing? A little slow today. People,
Okay.
guess there's still a minute left. Can you hear me? I may not talk as loud today because of a bit of a sore throat, but so if you can't hear me, just let me know. Confirm that you can hear me in this voice.
Yes.
Okay. Okay. So well, let's begin with a little review of lecture 15 because some things came up and in discussions on Piazza about the homework problems. So let's actually maybe revisit this general sufficiency condition. So which you proved in homework 4. Is not that hard to prove, but it turns out actually that in examples where you want to show that the solution that you found through the KKT conditions is a global minimum, it's quite convenient to use the general sufficiency condition to do that rather than using the second order conditions on the Lagrangian, and then separately making sure that if you confirm that something is a local minimum, then separately showing that it's a global minimum. But for the problems in which that approach works, it turns out that actually the general sufficiency condition is a slightly easier way to get to the same answer. Okay. So that's what I changed the post lecture notes for lecture 15 to reflect that. So please download the new version. And the way I did it was I put the general sufficiency condition up front rather than waiting till the end of the lecture. So because it's useful in the examples that come up. So and in particular, I also added a little note here to the end of this, said that if S is a convex set, so this constraint set, these S that contains additional constraint. By the way, one thing that we kind of glossed over in this class, I did that on purpose just to not get too technical with these things. But sometimes the function f and also these constraint functions, possibly not any example that you've seen in class, in all the examples that we've seen so far, these constraint functions are defined for all x belonging to Rn. But the objective function in some examples, when they're logged, okay, they may not be defined for all x belonging to Rn. So that's called, so the values of x for which the function is well defined is called the domain of f. You might have studied that in some class early on, some math class. And so this S could actually correspond to the domain of f in some examples. Okay, it could be other constraints too, but it could also just be the for example, if you have log of xi, right, and that's only defined for xi if positive, so that this S could correspond to xi as being positive, right? So that's another way to think about this additional constraint set S, especially when you apply the general sufficiency condition. So if this S is a convex set, which domains are typically going to be convex, okay, and F is convex, HIs have to be affine for things to work out. So the HIs are affine. Affine means linear plus a constant, right? Think of it, I mean, a lot of people call these when you have a constant in a linear function, you still call it linear, but to be technically correct, you should call it affine. And if the Gj is a convex, then it's easy to see that the Lagrangian function, which will be fx plus lambda times hi. So the thing is that lambda could be positive or negative, so hi has to be affine for for it to be convex when you multiply by a positive or negative. HIs can't just be generally just be convex. It has to they have to be affine. But the GIs can be convex because they're always going to be multiplied by a non-negative Lagrange multiplier. So when you add those things up, you get a Lagrangian function that's going to be convex in X. Okay, and so for a convex function, if you verify that the gradient is 0 for some X star, then that X star has to be the global minimum. That's sufficient. If there exists X star such that the gradient is 0, that's the minimum. Okay. That's a minimum in general, but if it's unique, it's a unique global minimum. Okay, so and you usually verify the way you find X star using KKT conditions is by using this gradient condition. So you already have this condition satisfied for X star. So if your L is convex in X, you're done. You already found the global minimum. You don't have to do anything else. So that's how we can apply this in the examples, and that's much easier than using the fact that the F might be convex over a convex set, which is also true, but then you have to do a little bit more work to verify, which I kind of glossed over in class, to verify that the gradient of F at X star times X minus X star, dot product of X minus X star is non-negative. That's what we saw in lecture 10. That's a necessary and sufficient condition, which is also very easy to check in these examples, by the way. But I think I realized after the fact that maybe in all of those cases you can just apply the general sufficiency condition because L is going to be convex. Okay, so that's what I rewrote the part that last part of this example, and in fact this is why I sent you an email yesterday, so that in your homework problems you could do the same thing. That we can easily see that in this example L is convex, and we already verified that X stars actually found X star by setting the gradient of where is that? This is the case, right? Yeah, this is the case. We set the gradient of X mu to 0 to find X star, so it satisfies the gradient of Lx mu equal to 0, so it must be the global minimum. Okay, the same thing with the next example. The next example, the power allocation example. Here we have to be a little bit careful because we have an S which is not the entire space Rn, and the reason is that the domain of this function is not the entire space Rn. So if you look at the power allocation problem, this function f is only really well defined if 1 plus xi divided by sigma I squared is positive, right? Greater than 0. So so you can think of S as that. So you can think of adding a constraint to this. So you can add a constraint that basically that X belongs to S, where S is the set of X's for which 1 plus xi divided by sigma I squared is positive. I kind of glossed over that because it's I kind of implicitly assumed that the optimization problem is defined over the domain of domains, or the intersection of the domains of these functions. The G's in this case are all well defined for all Rn. It's only F that has this log that you have to worry about this. So you could take that, but I mean this is easily seen to be a convex set, so you don't have a problem with that. So then you basically all you have to do is check that Lx mu is convex over its domain. Oh, the domain is just this S. Okay, and it's easy to see that it's convex. And so by the general sufficiency condition, X star is equal. Okay. So any questions about applying this general sufficiency condition to prove, to find a global minimum in these kinds of examples where the function is convex, so the h's are linear or affine, and the g's are convex. Then it's a very easy problem. And in most examples that you will encounter in this class, okay, that would be the case. Okay, so there are some examples we looked at with equality constraints where the h's were not affine, and so you don't have a convex problem, or the f is not convex. But then you have to use other tools. Then you have to use things like coercivity or something to, and then use a second order condition along with coercivity. But if you have convexity, things become much simpler. Okay. Any questions? All right. So you're sure you don't have any questions, right? Well, we've discussed this a lot on Piazza as well, so I hope there aren't any remaining questions.
Can we say anything about the uniqueness of the global min under these
conditions? Yeah, if it's strictly convex, it'll be unique, right?
Yeah.
Yeah. And in all of these examples, they're actually strictly convex. So.
Okay.
If any of those functions is strictly convex, it's going to be, that's not true, because you could have some of these things being, some of the multipliers being 0. But certainly if f is strictly convex on S, then if you add anything to it, it'll still remain strictly convex, right? Add any other convex functions to it, it'll remain strictly convex. So, and that's true in these examples. All right, so now let's go to the last lecture where we were talking about what did we talk about in the last lecture? Barrier method. So here, this was a computational method to solve inequality constraint problems. That's right, right? This is what we were talking about last time, or did we say something else? Oh yeah, we did. Yeah. So this was another way to do the power allocation problem. And here, actually, we use the general sufficiency condition, but we used it in a slightly different, clever way to avoid, having so many constraints to deal with. Okay, so we took care of some of the constraints in the set S. And in this case, actually, the set S also make it, on this set S, the log function is well defined. So we didn't have to worry about the domain of the function. Okay. So yeah, I mean, if you look at textbooks, some textbooks, I mean, the textbook that Bertzikis' textbook tries not to talk about the domain of the function unless it's relevant. Okay, otherwise it's assumed that the domains of all these functions are the entire space Rn. Okay, whereas other books like the Boyd and Vanderburgi book, they start talking about domains of these functions and so on from the start, and define lots of get into a lot of mathematical details, which I think are not that relevant for many of these problems, and it just causes more confusion, which is why I chose not to bring that up unless it's relevant. Okay. But when you have logs, you do need to worry about whether the function is well defined on all of Rn or not, because it's not. Okay, so that's what we did. And here we directly applied the general sufficiency condition to find the global minimum. Okay, then we start talking about the barrier method. So the barrier method was a computational method to take care of inequality constraints for, and the basic idea is behind the barrier method is that uh, gradient descent kind of procedures have a problem if uh, if the minimum occurs on a boundary. So you basically make sure somehow you modify the problem so the minimum never occurs on a boundary, right? So you add this barrier function that blows up at the boundary, and then you make sure that the barrier function plays less and less of a role by multiplying that barrier function by an epsilon. So that's what we did here. So this function f could have a minimum on the boundary, but once you add the barrier function, you're not allowing it to have a minimum on the boundary. Okay, so if the minimum of this combined function is in the interior point, you can find that solution using gradient descent, and then you successively make epsilon smaller and smaller so that you approach the solution to the problem, to the minimization of fx, if of course if the original problem had an internal minimum, then you didn't even need to use the barrier method. But if it could, in most interesting cases, this function is going to have a minimum on a boundary, and for those boundary points, you can take care of you can take care of that using the barrier method, right? That's what we saw, and we proved that if you look at the a limit point, so if the sequence has a limit point x bar, then that x bar has to be a global minimum of my original problem. Okay, so we showed that last time. So actually, let's do a quick example to illustrate this. Okay, simple example. And this is from your textbook, and there's a nice picture as well if you want to take a look. So we're looking at okay, right. So we have this function here, and it's a quadratic. Actually, you can easily guess the answer that the value this function is minimized. Okay, because you want to make these things as these x1 squared and x2 squared as small as possible. So you can immediately guess that the solution to this minimization problem, if x1 is strictly bigger than 2, is just setting x1 equal to 2 and x2 equal to 0. Okay, so that's not hard to see, but we can actually prove this using KKT conditions. Let's do it formally, just to convince ourselves that that's the right answer. Okay, so here our constraint function g of x is 2 minus x1 in this case, right? And our Lagrangian is fx plus mu times gx. There's only one constraint, so there's only one mu. So we have to consider the possibilities now, two possibilities, a constraint being inactive and active. So let's first say that it's inactive. So mu equal to 0. Then the Lagrangian being 0 is the same as saying that the gradient of f is 0. But the gradient of f, it's easy to see that the gradient of f is just x1, x2. So the gradient of f being 0 implies that x is equal to 0. 0, 0. But this x does not satisfy the constraint, right? Does not satisfy the constraint that x is bigger than 2. So this is not feasible. Okay, so now let's go to make the constraint active. So mu equal to sorry, mu is not necessarily 0. Okay, so now we use the Lagrangian to find what x star and mu are. So if you set the Lagrangian to 0, the first component of the gradient is x1 minus mu, which is we set to 0, and the second component of the gradient is x2 set to 0. So with this implies that, and also we have the constraint that gx is equal to 0, it's active. So that says that x1 minus 2 is equal to 0, or x1 equal to 2. Okay, so x1 is 2, x2 is 0. So x star is 2, 0, like we guessed earlier, and mu equal to 2. So this satisfies the KKT. And mu is positive, like it's non-negative, it should be non-negative, it's all good, right? But in this case, of course, Lx mu is strictly convex. That's easy to see, right? F is a strictly convex function, and the constraint is constraint function g of x is linear, which is a special case of a convex function. So this the sum is a strictly convex function r squared. So by generally sufficiency condition, this x star is the global minimum for the problem. Okay, so now let's see what happens if we apply the barrier method to this problem. Okay, and let's just confirm that the barrier method is going to the right answer. So let's look at let's take the logarithmic barrier in this case. So it's negative log of minus g of x, right? That's a logarithmic barrier. So in this case, it's minus log of x1 minus 2. And at the kth iteration, we're finding xk, that's the minimizer. We can write this as argmin. Argmin is the value of x that minimizes the fx plus epsilon times bx. Okay, that's the notation. And incidentally, we use this set notation here because it may not be unique. So the xk belonging to argmin says that xk is one of the solutions that minimizes. That's the notation. Okay, and of course we have a constraint for the barrier, because the barrier is not well defined for x equal to 2. Actually, x less than or equal to 2. So we have to minimize under the constraint, right? So we have half x1 squared plus x2 squared coming from f of x, and then epsilon k times the barrier. Okay, and we can call this function g k of x. Might remind you of some notation we used before when we proved the Lagrange multiplier theorem, right? Equality constraints. So this g is easily seen to be a convex function over the domain, x is one bigger than 2. Yeah. And of course, this domain is easy to see that the domain is a convex set. Okay, so this g function is convex over a convex set. And why is it convex, by the way? Because this is a strictly convex function. This is strictly convex. This log, negative log is also convex, right? So we can find the solution to this problem by just taking the derivative or the gradient of g, right? So let's do that. So g is given by this. Let's take the gradient, set it equal to 0, and we get that x1 minus the gradient respect to the derivative respect to x1 is this. Set that equal to 0, and then the derivative respect to x2 is just x2. So get that. So from that first equation, we get that x1 squared minus 2x1 minus epsilon k is equal to 0. So this means that if you solve this quadratic, something you did in high school, you get that this is a solution plus minus, but x1 cannot be negative because it's not feasible. So we can get rid of and we can get rid of that, and we just get 1 plus. Okay, so the solution to minimizing gk, the barrier with the barrier, we get 1 plus square root of 1 plus epsilon k is 0, which as k goes to infinity, epsilon k goes to 0, and xk converges to 0, like it should, which is x star. Okay, so we just confirm that the barrier method works for this example. Okay. But in general, we know that it works because we have a proof. Right? So, any questions? So the barrier method was useful to take care of inequality constraints. Okay. What about equality constraints? Of course, you can't apply the barrier method with equality constraints, because what happens? I mean, there's nothing like a boundary there, right? It's all boundary. So, you can't make things blow up at the boundary, because it'll just blow up everywhere on the constraint. So that's not a useful technique. So there's another computational method for solving problems with equality constraints, which, by the way, if you have a method that works with equality constraint, it can also be applied for inequality constraints. We know that because we can always convert inequality constraints to equality constraints. We saw that when we looked at the KKT theorem, right? So in some sense, this method is more general. So this is called the penalty method.
What's the drawback for the barrier method?
Oh, it's just that you can't apply it when you have equality constraints, right?
I see. Yeah.
But sometimes, you can justify relaxing equality constraints to inequality constraints and then apply the barrier method. That's a different story altogether. So basically, that's going a little bit beyond what I want to talk about in this class anyway. So, let's look at this other approach to deal with equality constraints. So this is called the penalty approach. So here, the idea is to again add something to the objective function. Okay, and that something that you add should be such that in some limit, the effect of that addition goes away. Okay, so here instead of taking a sequence of coefficients that goes to 0, we take an increasing positive sequence. Okay, so ck is an increasing positive sequence, and let ck go to plus infinity. As k goes. And here we solve for xk to minimize fx plus ck times h of x squared. Okay, and let's call that pk. So the original problem is this: minimize fx with these constraints. Here, you're going to take these constraints somehow and put it into this penalty function. So this might look a little familiar. This is the technique that we used in proving the Lagrange multiplier theorem. Okay, we absorbed. So this penalizes by making CK large, and you're trying to minimize, you're penalizing any violations of the constraint that hx must equal 0. Okay, so by the way, this hx is just a vector version of the hi x's. So hx is just all the hi x's put into a vector. So the norm of hx squared is simply the sum from I equal to 1 to m of hi of x squared. Okay. So you can see that as I increase my ck to infinity, the effect of this will start to go away, and you're going to just be going to be minimizing fx. But basically, it will only go away if this hx is close to 0, right? Or it's tending to 0 as k goes to infinity. And we'll see that that's exactly what happens if we solve this and we let xk be the solution to the kth problem, pk, then that xk satisfies that condition. Xk will go to a limit such that that limiting value h at the limiting value is 0, so that you satisfy the constraint and you minimize f of x in the limit. Okay, and we'll see that in just a second and prove this. So that's the result. This is similar to the result we had for the barrier method. Okay, we say that every limit point of xk is a global minimum for p. And again, just like in the barrier method, we need this S to be closed. And closure is really needed because you want the limit of the sequence of these xk's to go to something that's still inside the set. Okay. All right. So let x bar be the limit, that just like we did the barrier method, over on some subsequence we'll call script k. Okay, so and let f star be the minimum of fx with the constraints, right? With the constraint x belonging to S and hx equal to 0. Okay, so that f star is the minimum value of the objective function. But so since hx is 0, right? If I'm minimizing with hx being equal to 0, this is the kind of the trick that we used also in the proof of the general sufficiency condition. We can add this, and it doesn't change anything because under the constraint, this is already 0. So I've not changed fx. So these are the same problems. But now what I'm going to do, again, similar to the trick we used in proving the general sufficiency condition, we'll remove one of these constraints. When you remove a constraint, you're minimizing over a larger set, so that minimum value will be smaller, right? Can't be larger. So I just keep the constraint that x belongs to S and remove the constraint that hx equals 0, and I'll get a smaller value for the sum. Or not smaller value, but it can't be larger. So greater than or equal to. Okay. But this is exactly what we called xk, right? So xk is the minimizer for this sum. So this is f of xk plus ck times h of xk. So from this, we just rewrite this equation that we just derived. So we showed that f star has to be bigger than or equal to this. So I'll just take this to the left-hand side, and I conclude that this has to be less than f star minus f xk. For all k. So we'll call that 1. Okay. Now, by continuity of f, we know that the limit of f of xk has to go to f of x bar, because on this subsequence. Right? So as k goes to infinity, if you look at the right-hand side of this function, the right-hand side of this function goes to some finite quantity. And let's look at the left-hand side. Left-hand side of this function, and this is actually almost identical to the trick that we used in the proof of the Lagrange multiplier theorem. So we have something here that's going to something finite, and it's upper bounding this positive quantity, whereas the ck is positive and going off to infinity. And so if this h went to anything other than 0, this thing will blow up, the product will blow up, right? So the only way this one can hold is if the limit of this left-hand side, limit of the left-hand side over the subsequence goes to 0. Now, by continuity of h of x squared, the limit of this guy can also be written as the norm of h of x bar squared. So this must equal 0. So in the limit, I'm meeting my constraint with equality with x bar. Okay, so we're almost done. So now what we do is we use the fact that S is closed. Since S is closed, xk belongs to S for all k means that x bar belongs to S as well, because the limit point will be in the set for closed set. Okay, and then we just showed from 1 that f star minus f of xk is ck times h of xk squared, which is a non-negative quantity, so that's true. So this means that f of xk is less than or equal to f star, sorry, which is the minimum. Now I take the limit of this over the sequence. So this is also going to be less than f star, but that limit is f of x bar. So now we have found an x. We see that x bar is in the set S. X bar satisfies the constraint, and the value of the objective function x bar is less than or equal to the minimum value that f can take over the constraint set. All right. So x bar belongs to S. H of x bar is 0, which means that x bar is feasible. and it has a smaller value than the minimum. So what does that say about X bar?
It is the minimum.
It is a minimum. So X bar is a global minimum. Okay. So we showed that something similar to what we did the barrier method, that if we solve the sequence of problems with a penalty included, then eventually we'll get to the solution to the original problem. Okay. All right. So actually, it's 11:40. Well, actually, let's finish this example, and because I want to do a different topic after the break. Okay. So let's do an example. This is the example from your exam, actually, right? You want to minimize this function subject to this equality constraint. And you know from your exam that 1,1, you may not remember this, but you can go back and look at it. But we showed that 1,1 is a global minimum for this optimization problem. So now let's actually solve this using the penalty method, okay, which will result in an unconstrained optimization problem. So we can write down the penalty function f of x plus ck times the constraint squared. Okay, and let's call that gk. We call that gk of x. And if you take the gradient of gk of x, you just get 1 minus 2x2 plus 2ck x1 plus x2 minus 2 for the first component. Second component, 1 minus 2x1 plus 2ck. It's symmetric in x1 and x2. Okay, and if you look at the Hessian, you get 2ck, 2ck minus 1, 2ck minus 1. By symmetry, this is also 2ck. So you get that. Okay. Now, so if you look at the determinant of this matrix, or the Hessian matrix, this is 2 times ck squared minus ck minus 1 squared, which is 4ck minus 2. Okay, so as long as ck is strictly bigger than half, I mean, we're taking ck to infinity anyway, so that's not a big deal to make it bigger than half. Then the Hessian is strictly positive definite. And why is that? Because, again, then if you look at the principal minors, essentially, so this principal minor is positive, and the determinant of the matrix will be positive if ck is bigger than half. So this will be a positive definite matrix. So xk is a solution. In that case, you can find xk by solving for the gradient. Again, we're being systematic about this because first we need to confirm, convexity through, in this case, we actually get strict convexity through the Hessian, and then we can solve for the gradient equal to 0. And if you solve for gradient equal to 0, you get a set of, it's a symmetric set of equations. Symmetric is x1 and x2. So the solution for x1 and x2 should be the same. Okay, and so if you plug in x1 equal to x2 in the first equation and solve, you get that x1 is equal to x2, which is 4ck minus 1 divided by 4ck minus 2. Okay, so that's my xk solution. And you can see here that as k goes to infinity, ck goes to infinity, and xk indeed goes to 1, 1, which is x star. So it's a confirmation of the result that we just proved. Okay. Again, this is a simple example, which is why we could easily show this. But in general, you can just call on the theorem we just proved. Okay. All right. So, any questions about barrier and penalty functions?
Can we say anything about the convergence rates of these methods?
Yeah. So that gets into some details. So it'll be based on how you take ck to infinity and so on. The textbook has a discussion on that, a little bit of a discussion on that, but I'm not going to say much about that here. Yeah.
Okay, thanks.
It'll also depend on specific examples too. So you need to put some conditions on the functions and so on. Okay. One comment I want to make before we take a break is that it turns out that in some examples, this kind of penalty function, just taking ck times h squared, can lead to ill-conditioned problems, especially if you have linear constraints, and we'll actually do an example of that a little bit later. And so, although it looks nice, you can end up with ill-conditioned problems for which gradient descent may not actually work that quickly. And in that case, what you end up you may have to do is add something else to this this optimization problem. Okay, and what you end up adding is related to the Lagrange multiplier. Okay, and so those kinds of methods are called augmented Lagrangian methods, or also just called Lagrange multiplier optimization methods. And we'll talk about that maybe on Friday next Thursday maybe, because next Tuesday is a holiday. So yeah, we might talk about that next Tuesday. But I wanted to introduce another topic before we get to that, because it's related, and that's duality. So after the break today, we'll start talking about duality, and I'll finish talking about at least what I want to say about duality on Thursday. Okay, so I'm going to take a short break now, unless you have any questions. Right, no questions, then let's take a break. I'm back at 11:50. Okay. All right. Time to talk about duality. All right. Okay. So let's look at this general inequality constraint problem. Minimize fx, x belong to s. S could be, as we said earlier today, S could also just correspond to the domain over which things are well defined. And we have equality constraints, or inequality constraints. You can define a Lagrangian. Okay. All right. With both the lambdas and the mu's. And then we can define a function which we'll call the dual function. The dual function is a function of lambda and mu, where what we do is minimize the Lagrangian over s over x. So minimize belong to s. So we get rid of the dependence on x, and we're left with some function that's a function of only the Lagrangian variables. Okay, and of course this function is defined on the set of lambda mu, because we want our multipliers to be valid multipliers. So lambda can be anything in Rn, but we require the mu's to be non-negative. Okay, and this is a convex set. Okay, so now this function d of lambda and mu, you guys can hear me, right? All good? Yes. Yeah, okay. So this function is defined on this convex set. Okay. What we're going to now establish is that this function is a concave function in lambda and mu. Okay, or the negative of this function is a convex function over this convex set. Okay, so let's look at that again. So dual function is to take the Lagrangian, minimize it over x, and look at the multipliers such that the mu j's are all non-negative. Okay, so the claim is that this d lambda mu is concave on this set. Okay, and to prove that, what we need to do is just verify the definition of concavity in this case. So let's take alpha belonging to 0, 1, and let's look at a convex combination of lambda mu and some lambda tilde, mu tilde that belong to this set. Okay, so that this function is a function of these two variables, lambda and mu, and that's given by the minimum. But we go back up here, is the minimum of the Lagrangian, right, corresponding to this variable. So it's a minimum of fx plus the Lagrange multiplier with this convex combination is lambda plus 1 minus lambda tilde transpose hx plus alpha mu plus 1 minus alpha mu tilde transpose g of x. So this is the Lagrangian with those multipliers, the convex combination of lambda, lambda tilde, and mu, mu tilde. So now, if you look at this minimum, this is all linear functions. So I can write this as the minimum of alpha times f of x plus lambda tilde h of x plus mu transpose g of x plus 1 minus alpha times the same thing with the tildes. All right. So now I have a minimum of a sum of two things, which are functions of x. This guy is one function of x, this guy is another function of x. The minimum of the sum of these functions, I claim, is bigger than the sum of the minima. And this is similar to the result we used earlier. We looked at the maximum of a bunch of convex functions, and we said that the maximum maximum of sum is less than the sum of the maxima. And this is the opposite. So the minimum of the sum is going to be bigger than the sum of the minima. Why is that? Anyone can give a quick explanation for why this is true?
I think the sum of the minima has more degrees of freedom because the x's aren't tied between the functions.
Yeah. Or another way of saying that same thing is that the minima of these two functions can occur for different values of x. So, okay, so the minimum of one of those functions can maybe happen at x equal to 1, and it's minus 10. And the minimum of the other function is minus 20. That happens at x equal to 2. But at x equal to 1, the second function, it doesn't achieve its minimum, right? So when you look at the sum of the functions, you're going to get something that's larger. So because these two functions can achieve their minima at different points, potentially. So this is always true. And so, but then if you look at what that is, that's just alpha times, by definition, alpha times d lambda mu plus 1 minus alpha times d of lambda tilde mu tilde. So what we've basically shown is that d corresponding to the convex combination is bigger than the convex combination of the d's, and so this means that d is a concave function, or negative d is a convex function. Okay. Are you unhappy with this proof? So this is a slight generalization of the idea of the minimum of a bunch of concave functions being a concave and the maximum of a bunch of convex functions being convex. All right. Okay, so if there are no questions about this, now let's talk about what duality is all about. So just for convenience, let's call the feasibility set F like we did before. And F is the set of all x's for which the constraints are satisfied. Okay. So what the weak duality result says is that if I look at the maximum of the dual function over the multiplier space, okay, it's less than or equal to the minimum of the function under the constraints. So these two optimization problems are related in the sense that the maximum of this function is always going to be less than or equal to the minimum of this function. Okay, so let's prove this, and then I'll talk about what this might mean. Okay, so let's say let's look at a lambda mu belonging to the convex set where all the mu j's are non-negative, and x belonging to the constraint set. Let's look at the Lagrangian function for these values of x and lambda and mu. So the Lagrangian, since this satisfies the constraint, hx is equal to 0, so this term goes away, and for x belonging to f, this term goes away, and this term is gx is less than or equal to 0, and the mu's are greater than or equal to 0. So this term is less than or equal to 0. So if we look at this whole sum, the sum, this is 0, and this is less than or equal to 0. So this sum is less than or equal to fx. Correct? On the set f, when lambda mu belongs to C and x belongs to f, this is true. Right. So this is true for all. This statement is true for all lambda mu belong to C and x belong to f. So if I look at the minimum over the set f, that will also be true for that, because it's true for every one of them, right? So if I take the minimum on the left-hand side, it'll still be true that that's less than or equal to f of x. Actually, it's also, I mean, and lambda mu belonging to C. But then I can take the minimum on the right-hand side, because it's true. This statement is true. The left-hand side is independent of x. The right-hand side depends on x. So this will be less than minimum x belonging to f, fx, for all lambda mu belonging to C. But this is what I'll call f star, right? Under the feasibility constraints. Now let's look at the left-hand side again. The left-hand side, I have a set F which contains, sorry, F is smaller than the set S, because F adds more constraints to the set S. You're also adding these other constraints. So F is a smaller set than the set S. So F is smaller than S. F is contained in S. So now if I look at a minimum over a smaller set, right, that's going to be larger than the minimum over a larger set. And we've used this argument before. So if I now replace F by S here, I'll get something smaller, so it'll remain smaller than F star. Less than equal to F star for all lambda mu belonging to C. Okay, but that, what's the left-hand side? That's exactly what we defined to be D. But this holds for all lambda. So d lambda mu is less than f or equal to f star for all lambda mu belonging to C, which means that I can take the maximum over lambda mu belonging to C of d lambda mu, and it'll still be less than f star, which is equal to the minimum of fx, x belonging to. So that's what we've shown. So we've shown that the maximum of the dual function d lambda mu over the multiplier set is less than or equal to the minimum of the original function. So this is the problem that we want to solve, the optimization problem that we want to solve, and we have a lower bound that we can obtain by solving this problem. What might be an advantage of doing this? What's special about the problem on the left-hand side?
Is that linear, so it's easy to solve on the left-hand side?
No, not quite linear. What do we show about this function d lambda mu?
Concave.
Convex.
It's convex or a concave function, right? So this maximization of this concave function is actually the minimization of the negative of that concave function, which is a convex function. So this becomes a convex optimization problem. Okay, it's always going to be a convex optimization problem, whereas this one may not be a convex optimization problem. So the dual is always a convex optimization problem. So a lot of powerful techniques can be used to solve this problem. But the issue is that you're not really getting a solution to the original problem by solving this problem, right? We're only getting a lower bound. But the whole reason for looking at the dual function is that there are many examples where you can establish that these two are equal. There's no gap between the gap between the solutions to these problems is called the duality gap, right? And for many problems, one can establish that there is no duality gap. So you might be, in some cases, you might be able to solve a non-convex optimization problem using a convex optimization problem as a surrogate, and you can show that the solutions to these problems are the same. Okay, so we'll talk about that. Some conditions under which we have equality here. It turns out that the general conditions under which you have equality turn out to be cases where the original problem was also convex. But it's still interesting and useful to look at the dual problem sometimes, because the dual problem might have some advantages still. And the other reason is that you can develop iterative methods that somehow go between the solutions of the original. It's called the primal problem. This problem is called the primal problem. This is called the dual problem. So with that kind of shuttle between these two in order to get efficient iterative methods to find the optimum solution. Okay, then those are called primal dual methods. Okay, so we'll say a little bit about that on Thursday. I really can't get into, you could actually teach an entire optimization course on duality, which we obviously don't have time to do that. So all I've allocated in this course is 2 lectures to talk about duality. So I'll just give you the very high level, high level information about duality. And if you want to read more details, the textbook, actually, the later chapters in your textbook, use the power of duality in solving optimization problems more explicitly. Okay, but those are topics that I really can't get into, and the more researchy type topics, and they're also specific to applications. So in certain applications, you can show that there's no duality gap, and then the dual problem will play a significant role then. So, and in fact, some of you will be doing, those of you who are going to be doing research projects, you might come across some of these results in the papers that you look at. All right. So I need to form groups. So I think I sent you an email about that. So start thinking about forming groups of 3 for doing up to 3, a maximum of 3 students for doing your research papers. So and maybe after you're done with your computer assignment 2, I'll give you a little more information about what I expect you to do, which is not all that much. I just need you to read a few papers on an application that might be relevant to some research that you're doing as a graduate student, and report on that. So that would be the idea for the research paper. All right. Any questions about duality? We still have a few minutes. Or anything else we have covered so far?
Oh, I have a question.
Yeah.
If you don't know the minimum of f of x, how do you know the duality gap?
Oh, so you can prove that there is no gap without explicitly minimizing. So that's what we're going to show in the next lecture. So hold on until the next lecture. So it'll be based on the KKT conditions, essentially, without actually explicitly solving. But one thing to keep in mind is that the dual problem also, in order to find d lambda mu, you have to solve a minimization problem, right? You have to minimize the Lagrangian anyway. So look at the definition of d. So d is the minimum of the Lagrangian under these constraints on the parameters. And so in some cases you might be able to explicitly write down a form for that minimum. Okay, and so then the dual function can be written down explicitly, and once you have that, then you can use convex optimization techniques to minimize or maximize or minimize the negative of the dual function.
Just to check my understanding, so basically the standard procedure probably will first apply the KKT that we learned before to the right-hand side of the mean of the fx. If we can solve that, then we're good, right? Otherwise, we'll try to see if we can find like an upper bound of the Lagrange, the dual problem, and
dual problem, yeah,
if that can help. And
yeah,
then
that can help. It might help, especially in cases where the original problem is, well, even if the original problem is convex, it can still help because you can actually sometimes you get some interesting intuition from looking at the dual problem. Okay, and we'll say a little bit about that on Thursday, and also there may be iterative techniques that exploit the dual. And one application of that would be this augmented Lagrangian, or simple application of that is the augmented Lagrangian method, which we'll talk about next week.
And also another question is why it's called weak duality? Weak
duality because you don't have equality. And this always holds. Weak duality always holds. But then under certain other conditions, which we'll talk about. That's called Slater conditions. That's one set of conditions under which you have equality, and that's called strong duality.
Gotcha.
This terminology. All right.
There's a question in the chat.
Another question in the chat. Computer assignment 2. I thought they did assign other. So for computer assignment, are we sticking to the same groups? Well, some people did drop the class, so I think the TAs reassign students to groups. So you may want to check that, or check with the TAs. I thought they put the assignments on the web page. Let me just take a look. Does anyone else know about this, or check with the TAs? I mean, if all the students of your group are still there, then I think you can stick with the same group. Otherwise, yeah, I don't actually. They didn't put anything on the website about that.
They did. It's under right above the computer assignments, and they're the same except that they gave us all a time slot.
Oh, okay. I don't see the link to the spreadsheet on the web page. Oh, here it is. Yeah, yeah, that's right. So if you click on the things that says check the assigned groups and time slots here, that takes you to the spreadsheet. So you'll be able to tell your group from that. Yeah, you better know what your group is if the group has changed. Maybe because Monday is when you have to demonstrate that. It's not that hard to do the computer assignment because it's most of the code will remain the same as what you had in computer assignment 1, except you're going to be doing it with different parameters. That's all. Okay. Any other questions? All right. So talk to you guys on Thursday then.